Z-scores are used to determine if observations are outliers and used to compute the skew, which is a measure that indicates whether the distribution of the data is skewed or symmetric. The Z-scores can be used to compute frequencies, which can then be compared to Chebyshev's theorem and the empirical rule. The Z-score is often called the standardized value. I consider it to be the single most important concept in this course. The ith Z-score denotes the number of standard deviations the ith observation of variable x is above or below its mean. It is computed by dividing the ith deviation from the mean by the standard deviation. So it has no units. If variable x's units are dollars, the z-score tells us how many standard deviations the ith observation is above or below average. Whereas its numerator tells us how many dollars the ith observation is above or below the average. The numerator demeans the variable x, shifting the distribution's center from x bar to 0. Dividing by the standard deviation changes the standard deviation from some generic value s to equal 1. An observation z-score is a measure of the relative location of the observation in the data set. If you're looking at two variables, say personal income and age, the deviations from the mean cannot be compared because they are in units of dollars and years, respectively. Suppose your annual personal income and age are $8,455 and 19 years. If the sample means are $8,955 and 20 years, your deviations from the mean would be minus $500 and minus 1 year. Both indicate your income and age are below average. Which one is more extreme? The deviations from the mean cannot tell you this. In order to figure out whether your income is more extreme than your age, you need to divide the deviations from the mean by the corresponding standard deviations. Suppose the standard deviations are $1,000 and 0.5 years. Your income z-score is minus $500 divided by 1,000, which equals negative 0.5 standard deviations. Whereas your age z-score is minus 1 year divided by 0.5 years, which equals minus 2. Your age is 2 standard deviations below its mean, while your income is 1/2 of a standard deviation below the mean. Hence, your age is more extreme relative to your income. Using the sorted Hudson auto repair example, the z-score of the smallest value is equal to the deviation from the mean corresponding to the smallest value in the data set divided by the standard deviation. The smallest value in the data set is $52. The sample mean is 78.98, and the standard deviation is 13.99. The resulting z-score is negative 1.93. This value means observation $52, which is $26.98 below average, is 1.93 standard deviations below average. So 52 is not within 1 standard deviation from its mean, but it is within 2 standard deviations from its mean. Notice that we carried the first deviation from the mean and the first z-score from the previous slide into this table. The second deviation from the sample mean is computed by subtracting the sample mean of 78.98 from the second observation of x, $57. The second deviation from the mean is equal to negative 21.98. This means the cost of the tune-up parts on the second invoice is $21.98 below average. Dividing the second deviation from the mean by the standard deviation, 13.992, yields a z-score equal to negative 1.57. Hence, $57 is 1.57 standard deviations below the mean. The third, fourth, fifth, and sixth deviations from the simple mean are computed by subtracting the simple mean 7898 from the third, fourth, fifth, and sixth observations of x, all of which are equal to $62. These deviations from the mean are equal to negative $16.98. This means the cost of tune-up parts on the third, fourth, fifth, and sixth invoices are $16.98 below average. Dividing these values by the standard deviation results in third, fourth, fifth, and sixth z-scores, all of which are equal to negative 1.21. Hence, $62 is 1.21 standard deviations below the mean. Repeat this process for the remaining observations, but we only show the ones for the 7th, 49th, and 50th observations. The 7th, 49th, and 50th deviation of the mean are negative $13.98, positive $26.02, and positive $30.02. The corresponding z-values are negative 1, 1.86, and 2.15. Now, the sum of the deviation of the mean is equal to 0. The sum of the z-scores is equal to 0 too. This is because when we're calculating a z-score, the numerator demeans the variable. If we divide the sum by the sample of 50, the result is 0 as well. This means that the mean of any set of z-scores is equal to 0. In addition, since each z-score was computed by dividing by the sample standard deviation s, the sample standard deviation of any set of z-scores is equal to 1. This is why the z-score is called the standardized value. A data value that is below average will have a negative z-score. If you are a below average free throw shooter, your z-score is negative. A data value that is above average will have a positive z-score. If you're an above average free throw shooter, you will have a z-score that is positive. A data value that is average will have a z-score equal to 0. If you are an average free throw shooter, your z-score is equal to 0. As I said earlier, I believe the z-score is the single most important concept taught in elementary statistics. It can be used to help determine the shape of the distribution. A symmetric distribution will have a skew equal to 0. Left skewed distributions will have a negative skew, while right skewed distributions will have a positive skew. The formula for computing skewness for data is somewhat complex. Skewness is easily computed using statistical software. However, a skew is just the average, essentially, of z-scores if the sample size is large. Okay. So if the sample size is large, say the sample size is 1,000. This value here is 1,000. This value here is 999. This value here is 998. 1,000 is approximately equal to 999. So these two numbers here approximately equal 1. And 1 divided by 1,000 is about the same as 1 divided by 998. So when n is really, really large, the ratio of these two numbers goes to 1. And the value of the skew gets really, really close to this value down here. To compute the skew, we need to first compute the 50 z-scores for a Hudson Auto repair example, which we've already done. Remember, they added up to 0, and their standard deviation is 1. The first cube z-score is equal to negative 7.17. Now, notice that we're cubing a value. So we have a negative 1.93 times a negative 1.93, which is positive. We take that positive value and multiply it again by negative 1.93, and we get a negative 7.17. So cubing the z-score preserves the sign, the original sign of the z-score. The second cube z-score is equal to negative 1.57 raised to the third power, which equals negative 3.88. The third, fourth, fifth, and sixth cubed z-scores are equal to negative 1.21 raised to the third power, which equals negative 1.79. The seventh z-score is a negative 1. Negative 1 times negative 1 times negative 1 is a negative 1. Now we repeat this for the next set of observations, all the way down to the 49th. The 49th z-score is 1.86. Cubing 1.86 gives 6.43. The 50th z-score, 2.15, cubed is 9.88. The sum of cubed z-scores is equal to 22.567. Dividing this by the sample size of 50 yields an average cubed z-score equal to 0.451. If we take this 22.567, the sum of the cubed z-scores, multiply it by 50, divide by 48 and 49, we get a skew equal to 0.4797. So that means that the sample size doesn't have to be very big, 50, for the average cube z-score to be pretty darn close to the actual value of skew. A histogram is a bar graph, but a bar graph is not necessarily a histogram. The bars of a histogram have no gaps between them, and their widths are equal to the width of the intervals used in the frequency table. In the diagram below, the label on the y-axis says frequency. So we're constructing a frequency histogram. Since the frequency of interval 50 to 59 is 2, the bar corresponding to this interval stops at 2. Since the frequency of interval 60 to 69 is 13, the bar corresponding to this interval stops at 13. The frequency of interval 70 to 79 is 16. The bar corresponding to this interval stops at 16. The frequency of interval 80 to 89 is 7. The bar corresponding to this interval stops at 7. The frequency of interval 90 to 99 is 7. The bar corresponding to this interval stops at 7. The frequency of interval 100 to 109 is 5. The bar corresponding to this interval stops at 5. The total area of the red bars is 50. If this were a percent frequency histogram, the red bars would have an area equal to 100. If this were a relative frequency histogram, the red bars would have an area equal to 1. The histogram estimates the true distribution of tune-up parts cost. In most cases, we won't know the true distribution of this variable. The area under the true distribution is equal to 1 for the same reason that bars of a relative frequency histogram have an area equal to 1. Now the skew is approximately equal to the average cube z-score. If skew is equal to 0, the histogram will look symmetric. If skew is negative, the histogram will have a long left tail. If skew is positive, the histogram will have a long right tail. The sample size is 50, n minus 1 is 49, n minus 2 is 48, and the sum of cube z-scores is 22.567. The skew is equal to 0.497. Now that was really close to the average cube z-score of 0.451. That's because n equal 50 is quote-unquote large. Now larger the sample size, the closer the average gets to the actual skew. Now the mean was $78.98. The median was $75.50. The mode was $62. If the distribution was symmetric or had a skew equal to 0, these measures of central location would be all equal or really, really close to each other. If the distribution is symmetric, the histogram from a sample drawn from the population is probably symmetric too. The mean and median are equal, and the sample skew is equal to 0 or really, really close to 0. If the distribution is moderately skewed left, the histogram from a sample drawn from a population will likely be slightly skewed left too. The mean will be less than the median, and the sample skew will be between 0 and -1. If the distribution is moderately skewed right, the histogram from a sample drawn from the population will likely be slightly skewed right too. The mean will be more than the median, and the sample skew will be between 0 and 1. If the distribution is heavily skewed right, the histogram from a sample drawn from the population will likely be highly skewed right as well. The mean will be more than the median, and the sample skew will be greater than 1. If the distribution is heavily skewed left, the histogram from a sample drawn from the population will likely be highly skewed left too. The mean will be less than the median, and the sample skew will be less than -1. Chebyshev's theorem can tell you what the relative frequencies are for being within z standard deviations from the mean for any z larger than 1, no matter what the distribution of the data is. The value 1 minus the inverse of z squared is the relative frequency associated with the within z standard deviation interval. If z equals 2, z squared is 4. Dividing 1 by 4 yields 0.25. Subtracting this from 1 yields 0.75, which, according to Chebyshev's theorem, means at least 75% of the data values will be within 2 standard deviations of the mean. If z is equal to 3, z squared is 9. Dividing 1 by 9 yields 0.11. Subtracting this from 1 yields 0.89, which according to Chebyshev's theorem means at least 89% of the data values will be within 3 standard deviations of the mean. If z equals 4, z squared is 16, dividing 1 by 16 yields 0.06, subtracting this from 1 yields 0.94, which according to Chebyshev's theorem means at least 94% of the data values will be within 4 standard deviations of the mean. Most manufacturing processes are normal or bell-shaped distributions. For example, the volume that is in each 12-ounce bottle of Coca-Cola is normally distributed. Most of the time, the volume in the bottle will be slightly above or slightly below 20 ounces. Rarely will the volume be substantially less or substantially more than 20 ounces. According to the empirical rule, for data having a normal or bell-shaped distribution, 68.26 or about 68% of the data values are within 1 standard deviation of the mean. 95.44% or about 95% of the data values are within 2 standard deviations of the mean. 99.74% or nearly all of the data values are within 3 standard deviations of the mean. An outlier is an unusually small or unusually large value in the data set. Z-scores are used to determine if observations are outliers. A data value with a z-score less than -3 or greater than 3 might be considered an outlier. However, such a value could have been incorrectly recorded. For example, a person conducting a survey might have heard a respondent say 17 when she meant to say 70. Or the person conducting the survey could have recorded a response equal to 23 as 32 by mistake. A data value with a large or very small z-value could be the result of incorrectly including an observation in the data. For example, if you are studying female heights and weights, and a person you survey says they are male, but you think they said female, this could potentially contaminate your analyses because men tend to be taller and tend to weigh more. The large z-value or the unusually small z-value could be a result of an observation that was correctly recorded. In totem, z-scores reveal how data is distributed, while each individual z-value suggests whether an observation is an outlier or not. In the table below, for each of the 50 observations, we want to answer the question, is the observation within 2 standard deviations? If the absolute value of the z-score is less than 2, the answer to this question is yes. But the answer is no if the z-score is larger than 2. The first observation is within 2 standard deviations from the mean because the absolute value of its z-score is 1.93, which is less than 2. The second observation is within 2 standard deviations from the mean because the absolute value of its z-score is 1.57, which is less than 2. The third, fourth, fifth, and sixth observations are within 2 standard deviations from the mean because the absolute value of their z-scores is 1.21, which is less than 2. The seventh observation is within 2 standard deviations from the mean because the absolute value of its z-score is 1, which is less than 2. In fact, this observation is within 1 standard deviation of the mean. The 49th observation is within 2 standard deviations from the mean because its z-score is 1.86, which is less than 2. Everything between it and the 7th is within 2 standard deviations as well because the data are in ascending order. The 50th observation is not within 2 standard deviations from the mean because its z-score is 2.15, which is greater than 2. Because the observations were in ascending order, all but the final observations, whose z-score is 2.15, are within 2 standard deviations of the mean. Hence, 49 of the 50 observations are within 2 standard deviations of the mean, which is 98%. The empirical rule says about 95% of the observations are within 2 standard deviations from the mean, while Chebyshev's theorem says 75% of observations are within 2 standard deviations of the mean. Since the most extreme value is the maximum of 109, and it has a z-score of 2.15, all, or 100% of the observations are within 3 standard deviations of the mean. The empirical rule says nearly all of the observations are within 3, while Chebyshev's theorem says 89% of the observations are within 3. None of the observations in the Hudson Auto Repair sample data are outliers because the largest z-score in absolute value is 2.15, which is less than 3. Covariance and correlation are measures of how close the relationship is between 2 variables. Winning percentage of the football team and attendance at home football games are going to be positively related. Hence, their covariance would be positive, while their correlation would be close to 1. If these measures are computed using sample data, they are called sample statistics. If these measures are computed using data from the population, they are called population parameters. The procedure used to compute a sample statistic is referred to as the point estimator of the corresponding population parameter. When numbers are substituted into the procedure, the resulting number is a point estimate of the population parameter. The covariance equations are similar to the variance equations. Each deviation from x's mean is multiplied by the corresponding deviation from y's mean, which are then summed up. After summing the products of deviations from population means, the population covariance is divided by the size of the population, capital N. The result is a population covariance. If the sum of products of deviations from the sample means is divided by the sample size, the resulting statistic is a biased estimator of the population covariance. Dividing instead by degrees of freedom yields unbiased estimator of the population covariance. Reed Auto Sales has figured out that the more they advertise, the more cars they generally sell. According to the sample of data they have collected, the company sold 14 and 17 cars when it ran 1 TV ad. Sold 18 cars when it ran 2 TV ads, and sold 24 and 27 cars when it ran 3 TV ads. Sum of variable x's observation yields 10 TV ads. Dividing this by 5, the number of observations yields variable x's sample mean, which equals 2 TV ads. Sum of variable y's observations yields 100 cars sold. Dividing this by 5, the number of observations yields variable y's sample mean, which equals 20 cars sold. The 5 deviations from the sample mean of x are found by subtracting all 5 observations of x by x bar, which equals 2 adds. The square deviations from the sample mean of x are equal to 1, 1, 0, 1, and 1 squared adds. Summing up x's square deviations yields 4. Divide this by the degrees of freedom, 5 minus 1, yields a sample variance of x, which equals 1 adds squared. The square root of this is a sample standard deviation of x, which equals 1 add. The 5 deviations from the sample mean of y are found by subtracting all 5 observations of y by y bar, which equals 20 cars. The square deviations from the sample mean of y are equal to 36, 16, 4, 9, and 49 squared cars. Sum of y square deviations yields 114. Divide this by the degrees of freedom, 5 minus 1, yields a sample variance of y, which equals 28.5 squared cars. The square root of this is the sample standard deviation of y, which is equal to 5.34 cars. The products of deviations from the sample means are computed by multiplying the values of the x minus x bar column by the corresponding values in the y minus y bar column. The product of x's first deviation from the sample mean, minus 1, adds, and y's first deviation from the mean, minus 6 cars, equals 6 add cars. The negative times a negative is positive, which is why this is 6. The product of x's second deviation from the mean, 1 add, and y's second deviation from the mean, 4 cars, equals 4 cars adds. The remaining products of deviation from the sample means are computed in a similar manner, which are 0, 3, and 7 adds cars. Summing up this yields 20. Divide this by the degrees of freedom, 5 minus 1, yields a sample covariance equal to 5 adds cars. The scatter plot of this data is graphed in the diagram below, which has the number of TV ads on the x-axis and the number of cars sold on the y-axis. In the first observation, the car lot ran 1 TV ad and sold 14 cars. Second observation, the car lot ran 3 TV ads and sold 24 cars. In the third observation, the car lot ran 2 TV ads and sold 18 cars. In the fourth observation, the car lot ran 1 TV ad and sold 17 cars. In the fifth observation, the car lot ran 3 TV ads and sold 30 cars. The scatter plot explicitly shows that there seems to be a positive relationship between TV ads and cars sold. The relationship is not perfect. The plot of points do not lie on the trend line, but lie near it. The point corresponding to the means of the two variables, 2 TV ads and 20 cars sold, always lies on the trend line, which is also known as a regression line. Estimating the regression line is the focus of the final topic covered in advanced statistics. The covariance is difficult to interpret because its units are odd. Recall the units of the sample covariance in the Reed Auto Sales example. They were adds cars. What the heck is an add car? The correlation fixes this issue. The correlation is a measure of linear association, not necessarily causation. High correlation between two variables does not mean that one variable is the cause of the other. For example, hot dog sales at football games and the football team's winning percentage are highly correlated. This does not mean that the team will win more games if you sell more hot dogs at home games. A high winning percentage increases attendance, and high attendance increases hot dog sales. So winning percentage is the cause of attendance, and attendance is the cause of hot dog sales. The sample correlation coefficient is computed by dividing the sample covariance, S sub xy, by the product of sample standard deviations, S sub x and S sub y. The population correlation coefficient is computed by dividing the population covariance, sigma sub xy, by the product of population standard deviations, sigma sub x and sigma sub y. In the Reed Auto Sales example, the sample covariance, S sub xy, was equal to 5 ads cars. The sample standard deviation of x, S sub x, was equal to 1 ad. The sample standard deviation of y, S sub y, was equal to 5.34 cars. The sample correlation is the ratio of the sample covariance, S sub xy, and the product of sample standard deviations, S sub x and S sub y. The sample covariance was 5 ads cars. The sample standard deviation of x was equal to 1 ad, and the sample standard deviation of y was equal to 5.34 cars. The units of the statistics cancel out, hence the sample correlation coefficient is equal to 0.9363. In most cases, the closer the sample correlation coefficient is to positive 1, the closer the points lie near a positively sloped trend line of the scatter plot. In most cases, the closer the sample correlation coefficient is to negative 1, the closer the points lie near a negatively sloped trend line of a scatter plot. In this video, I'm going to demonstrate how to do simple regression using the data and example from Cengage Now question 1. In this problem, we want to know how winning percentage for a given season affects hot dogs sold for a randomly chosen game within that season. And the data are summarized in the table below. So I'm going to go ahead and copy the data to Excel. Now the first thing I'm going to do is I'm going to put the X in column A and the Y in column B. I'm going to flip row 2 to row 1. I'm going to do a little formatting so we can see the data better. Now the reason why I did that is because when you highlight data to scatter plot it, the first column Excel assumes are X values. The second column Excel assumes are Y values. So you have to kind of flip those. So to make a chart of how this relationship looks in a scatter plot, click on Insert, Scatter, click the one without any lines, and you can see that it looks like a upward sloping relationship. I'm going to delete that thing, and I'm going to format this so that the minimum value on the y-axis is what looks like about 70,000, right? So I'm going to format the axis. I'm going to choose 70,000 as my lowest y value. And I'm going to do the same thing for x, where it looks like the lowest value for x is probably 20. I'll just put in 20. And then I'm going to close out. Okay, now you can see it a little better, can't you? So the next thing we need to do, I'm going to kind of shrink this up a little bit so it's easier to see in the screenshot. I'm going to right click. I'm going to put my cursor over a data point. I'm going to right click. I'm going to add a trend line. I'm also going to display the equation on the chart. I'm going to display the R-square value on the chart as well. Hit close. So, Y, which is hot dogs sold, I can actually literally change that to H, And then I got 1307.2 times x, but that's winning percentage, right? And then I got this down here. This is the intercept. So that's the intercept. And this is the slope. And this is the r square. And I'm going to maybe make it a little bigger so we can see it better. I'm going to also get rid of the grid lines so we can see a relationship. So this line here, this black line, is the graph of this equation. If hot dogs sold is solely explained by winning percentage, then theoretically you could use simple regression, which is what we use in this Engage Now problem. In simple regression, the regression model is the equation that describes how the observed values of y relate to the independent variable and error term. So right here is the error term, which cannot be known, which is why we use the Greek letter E, epsilon. The slope, beta 1, which we cannot know, which is why we use beta. And the true intercept, which we cannot know, which is why we use beta again. The regression equation is the equation that describes how the mean value of y, denoted E of y, which stands for the expected value of y, is related to the independent variable x1. One of the regression model assumptions is that the mean of the errors is 0. So when you add up these errors, you get 0. When you divide by the population size, you get 0 divided by capital N, which is 0. So the expected value of the error is 0, and that's why epsilon is missing in this equation. The estimated regression equation is the equation that describes how the predicted value of y is related to the independent variable. Now notice that we use B0 and B1 here. We don't use beta 0 and beta 1 anymore. And the reason why that is because we've taken sample data. In this case, we have 5 observations. We've taken sample data, and we've used Excel to estimate the values of beta 0 and beta 1. The estimate of beta 0 in our example here is 35,534. If the sampling is random, then we expect this value to be near the true value, which we can never know, beta 0. So B0 is 35,534, which is an estimate of beta 0. We cannot know beta 1. If our sampling is random and our sample size is large, then we expect the slope here, the estimate here, 1,307.2, to be close to the true value of the slope, beta 1, which again cannot be known. So B1, 1307.2, is an estimate of beta 1. B0, 35,534, is an estimate of beta 0. So B0 and B1 are like X bar and S, and beta 0 and beta 1 are like sigma and mu. Back to Cengage Now, question 1. Part A says, use Excel to estimate B0 and B1 to 2 decimals. In our chart, we have 1 decimal for the B1 and 0 decimals for the B0. So what we're going to do here is we're going to actually conduct a regression analysis. This is the chart version of it, which has very limited information. We're going to do the full regression, which is going to be presented in a table. The way you do that is you go to Data, Data Analysis, scroll through until you see Regression, and you want to click here and then push this button to load your Y values. When you load your Y values, you want to include the label hot dog sold and then the 5 hot dog values below it. Then you do the same thing for the X range. You click on that white area, click on that button, include the label and the 5 observations below it. Because we've included the labels, we need to click labels. I like to put the output right below the table, or right below the data. Now when you click output, you got to click this white area because for some reason Excel will put you up here. So when you click output range, click that white area. I also like to get the residuals whenever I do a regression. So I have output range, labels, and residuals all clicked. I click the white area, I click this button here, and I'm going to put the output right there. And then I'm going to hit OK. Now I'm going to do a little cleaning here. I'm going to reduce the number of decimal places to maybe 3. So I highlight all of these numbers with lots of decimal places. I'm going to reduce the number of decimal places to, say, 3. And I'm going to do that same thing down here. Okay. I'm also going to get rid of this part of the table. Okay. So notice that we have what is called R squared in our chart. That value is identical to the R square in the regression summary table, 0.811. The standard error of the regression is just over 4,335. The phrase standard error shows up in the regression summary table. It also shows up in the coefficient table. These standard errors are the standard errors of these coefficients. So you can think of these as X bars, and these are the standard errors that are associated with these X bars from a Chapter 9 one-mean test. And then the t-stats are just the ratios of these two values. If I divide this number by that number, I get t-stat. If I divide this number by that number, I get t-stat. And these are the p-values that are associated with this t-stat. These are, by the way, two-tailed p-values. And you can compare these to an alpha from a two-tailed null hypothesis test. The F statistic is interesting. In simple regression, it is simply the square of the coefficient test statistic. So if I square the coefficients test statistic, I get the F stat, which is interesting. And the F stat is used to test for model significance. The T stat is used to test for coefficient significance. And because there's only one X variable in here, that one X variable comprises the model. So when you do a coefficient test in simple regression, you're doing the model test because there's only one independent variable. Notice that the p-value of the f-stat is the same as the p-value of the t-stat. Again, for that same reason. The model comprises one independent variable, winning percentage. So the t-test of coefficient significance is equivalent to the model test in simple regression. Now we have all the information we need to answer the questions from Cengage Now. I'm going to go ahead and reduce these to 2 decimal places, and I'm going to copy the estimate for beta 0, known as B0. I'm going to copy that into Cengage Now. I'm going to copy it there, and I'm going to copy it here. So I've copied the estimate of beta 0 into this box for B0, and then in this box for the intercept. I'm going to do the same thing with winning percentage. I'm going to copy that value and paste it into B1, and this B1 is the estimate for beta 1. Because it is the estimate for beta 1, it is the slope of this equation. This equation looks very similar to the one in Excel, in the chart. Let's see if I can get this on one screen. Okay, so I got y hat. Remember, y hat denotes the predicted value of y. In this case, predicted hot dog sales. It equals the intercept, which is identical to this number here, which is only to 0 decimal places, plus the slope times x. In this case, x is winning percentage. So that equation there and this equation here are equivalent. Now in part B, we want to enter the following information. The coefficient of determination is the R square. And we can get it from the chart, or we can get it from the regression summary statistics table. And R square, the coefficient of determination, to 3 decimals is 0.811 in my problem. The standard error of the regression is found in that same table. Excel calls it the standard error, but it's actually the standard error of the regression. I want to reduce this to 2 decimal places. Then I'm going to paste it right here, standard of the regression. The residual degrees of freedom are found in the ANOVA table of the regression output. So I have degrees of freedom in this column. I have the regression degrees of freedom, residual degrees of freedom, and total degrees of freedom. The residual degrees of freedom are 3. Why is that? Well, we had 5 observations, and we've estimated 2 parameters, beta 0 and beta 1. 5 minus 2 is 3. The estimated coefficient of the regression model is that value. This is the estimated intercept. This is the estimated coefficient. Don't let that confuse you. So the slope shows up 3 places. The estimated slope shows up these 3 places in our problem. The standard error of the regression, the standard error of the coefficient, is the value that is just to the right of the estimated coefficient. In part C, we're going to conduct the test of coefficient significance using 2% significance. The null hypothesis is beta 1 equals 0. The alternative hypothesis is beta 1 less than or greater than 0. Because the significance level is 0.02, and this is a 2-tail test, we divide the significance level alpha by 2, so in this case 0.01. And that is the column of the t-table. We had 5 observations, and we estimated 2 parameters, beta 0 and beta 1. So the degrees of freedom are 3. So we're in row 3 of the t-table. So when you go to row 3 of the t-table, and you're in column 0.01, the critical value is 4.541. So we have a negative 4.541 and a positive 4.541. And we have 2 critical values because we have a 2-tailed null hypothesis test. The t-stat, remember, is just the estimated coefficient, B1, divided by its standard error. those values are right here. So 1307.24 and 364.19. If I take this B1, the estimate for beta 1, and divide by B1 standard error, I get a t statistic of 3.589. And since the t-statistic is in the do not reject region, the null is not rejected at 2% significance. Using the p-value of the test statistic, 0.037, notice that 0.037 is bigger than the alpha level of 0.02. Because the p-value is bigger than the alpha level, what that says is the probability that if you draw a line straight up to here, and then over here you draw a line straight up from negative 3.589 to here, the area to the left of this value over here, and the area to the right of this value over here is the p-value, in this case 0.037. So when the p-value is big, as it is here, big relative to the alpha level, when the p-value is big, the t-statistic is close to 0. That is, the t-statistic is under the hump of the t-distribution, suggesting the coefficient is insignificant. So, in other words, when the p-value is big, the t-stat is close to 0. When the t-stat is close to 0, it is inside its critical values. When the t-stat is inside its critical values, the estimated coefficient is said to be insignificant. Going back to Cengage now, we can now answer part C. The critical value is plus or minus 4.541, correct? That's from our table. Dividing the estimated coefficient by its standard error, we did that already, gave us 3.589. We're going to do that to 2 decimals, so this would be 59. The estimated coefficient's test statistic that appears in its regression table is 3.59 to 2 decimals. Because the null hypothesis for the test of coefficient significance is not rejected using my data, we can say winning percentage has no effect on hot dogs sold. The coefficient of determination, which was 0.811, can be converted to a percent by multiplying it by 100. So the coefficient of determination implies 81.1% of the variation in the y variable. In this case, the y variable is hot dogs sold. 81.1% of the variation in the y variable, hot dogs sold, is explained by the model. In this case, the model is winning percentage. Now we're going to double check our work to see if we got all the questions right. And we did get all the questions right, which gives us a really nice warm feeling inside.